Assalamu alaikum, dear student. This is lecture number 1 of week number 8, and we are continuing the chapter number 7, dimension analysis. In the previous lecture we discussed about the learning objective of this chapter. Let's see up to what extent we have covered. So far we have studied the Buckingham Pi theorem to develop a dimensionless variable for any flow situation or for any real life problem of a fluid flow. So here now we are going to discuss that how we can use a dimensionless variables or dimensionless group or parameter in analyzing the data, and also how we can use a concept of modeling and similitude to develop prediction equation with the help of dimensionless variables. So let's see the topics we are going to cover today. The topics we are going to cover today are modeling and similitudes, theory of models, 3 basic law of similitudes, common dimensionless group in fluid mechanics, and finally the practice problem that we will do based on the theory we will discuss in the today's lecture. So basically these are the topics that we will study in this chapter. So I will start from modeling and similitude, and let's see up to what extent I am able to complete the lecture. So if the topic remain, I will discuss in the next lecture. So let's start with the modeling and similitudes. So far we have learned that how to develop a pi term or dimensionless group for a particular problem, and we have already discussed with the problem with a single pi term or 2 pi term or 3 pi term. So far if we have a single pi term, so we can easily describe the characteristics of the system, and even if we have a 2 pi term, that is also very easy to describe the characteristics of a particular problem or the system. But if we have even 3, we can describe the flow characteristics, or we can develop the graph or chart by using the experimental data. But if we have a more than 3 pi terms involved in a problem, then it is feasible to use model to predict specific characteristics of the system. So it would be difficult to use directly an experimental data by using a 4 pi term to describe the characteristics of a system. So instead of that, we are introducing another method to describe the characteristics of a system, that is modeling and similitudes. So what exactly it is? In experimental fluid mechanics, we sometimes cannot work with real sized object, okay, so known as prototypes. So instead we use scaled down or up version of them called models, okay. The concept of similitude is often used so that measurements made on one system model, for example in the laboratory, can be used to describe the behavior of other similar systems prototype outside the laboratory. Also, sometime in experiments we use fluids that are different than actual working fluids, okay. So this is also a very important point to note down. Also, sometime in experiments we use fluids that are different than actual working fluids. That is, we use regular tap water instead of salty sea water to test the performance of a marine propeller. So here you can see some pictures showing that wind tunnel test of an airline, and also the race car being tested in a water tunnel. The concept of modeling and similitudes are very helpful to solve the real life problems. In many cases, we don't want to build or develop a real size object, instead of that, because we are not sure that whether this will work or not after spending so much money, if it is if the system is very costly. Suppose if we are developing a new ship, submarine or aeroplane or high-rise building, so what exactly the problem with all those objects, we really don't know. So how we can save our time, our effort and money. So modeling and the concept of modeling and similitude help us a lot in this case. Here you can see we have two pictures of a wind tunnel, where you can see there is a aeroplane, there is a model of an aeroplane, and there is a water which is tested in a water tunnel, not the wind tunnel. Okay, so the reason is, here the important thing in the modeling and similitude is the size. How do we select the size of the model? Because you see, if we are not going to build a real size object, so what should be the size of the model? So that is basically depending on the testing facilities available in your area, or where you can test your equipment easily, or the testing facility that you can develop for that model. So based on that, basically we select the size of the model. And also you see, for example, you are making a ship, but the ship not only sail in the sweet water, but it also sail in salty water, in sea also. But some of the area, suppose you are living in an area where you have only sweet water, so how would you test the ship for the salty water? So in that case also we use different fluid, different scenarios. Okay, so how you will develop a similarity? Okay, how you will transfer the effect of sweet water to a salty water? So here you can see the racing car, because you see in the wind tunnel you do not have a facility to develop such strong wind, okay, through which a car passes. So in that case we are using water tunnel, where it is facing a lot more resistance, okay, comparing to the wind tunnel. But that car has to be travel in the atmospheric condition, not in the watery condition. Okay, but because you see the facilities is not available, okay, the amount of strong air or the wind we are not able to develop in the wind tunnel. So we are testing this car in the water tunnel. That can in the water tunnel we can achieve that much drag force, okay, or that much resistance we can achieve in the water tunnel. So normally the model is smaller than the prototype. Okay, so we will study now the procedure for designing models that will behave similar to its prototype. So how would we make sure that the model you are developed and the test you have performed, that will be exactly applicable when you develop a prototype? Okay, so let's see what is the method or procedure that when you will design a model, okay, and when you develop a prototype, so it will work exactly the model behave. So let's see the method or technique that the model will exactly behave the way its prototype will behave. Okay, so so what's the technique? The theory of model is developed by using the principle of dimension analysis. Okay, so the technique we have learned so far to develop a dimension analysis or dimensionless parameters, we are using the same principle. Okay, so any given problem, here you can see, for any given problem can be described as the functional form of the pi terms. So you know that whatever the real life problem we have, or whatever the object we have developed and we want to test in air or water or in any environment, so first of all we have to develop the dependent and independent variables, and after that we develop the number of pi terms or number of dimensionless variables or parameters. Okay, the number of dimensional parameters reduces the number of variables, so it reduces the variables in the form of number of dimensionless parameters. Okay, so here you can see, so these are the number of pi terms in the form of function. Okay, so pi1 is basically have the dependent variable. So these are the dimensionless variables or pi terms for the prototype or for the real life problems. Okay, for the real life variables. Okay, so the above equation describes the behavior of a particular prototype. So this equation is basically describes the behavior of prototype. Okay, the real life object, and a similar relationship can be written for the model of this prototype, and the same relationship. Okay, so this is the relationship for the prototype, and the same relationship can be written for the model. So this is pi1, so this is pi1 model, this is pi2 model, this is pi3 model, and whatever is the number of pi term, it can be written in the form of model, in the form of models. Okay, so this is the pi term for the prototype, and this is the pi term for the model. This just the same the pi terms or the pi group or the dimensionless group, exactly the same for the model we have for the prototype. So just we are considering this is for the model, this is for the prototype, and this is for the model, so that we should know that if let's see further. So here we can see that pi1 is equals to pi1 model, pi2 is equals to pi2m model, pi3 of prototype is equals to pi3 of model. Okay, so now the above conditions are called model design conditions or modeling laws. Okay, so these conditions are called modeling laws. These are the conditions that how we design the model. Okay, so let's take an example. So consider the example 7.1 of your book. Okay, so just open your book and see the example 7.1. In the example 7.1, okay, you see the drag force is depending on these variables. For a square, for a rectangular plate, the plate has a width w, height h, mu is the viscosity of the fluid, density of the fluid, and velocity of the fluid. Okay, and the drag force received by the plate. Okay, so here we have written the variables in the form of dependent and independent form. So the drag force is the function of all these variables. So now what is our next step? Next step to find out the number of pi terms. So we know all the procedure to develop the number of pi terms. So obviously if we have a if we are using a repeating variable method, so we have a we have 6 variables. So in that case, if we are going to use MLT system or FLT system, so we can easily see that we have a 3 basic reference variables. We have a 3 basic or fundamental quantities, okay, MLT or FLT we can see here, and if we follow that method only, we can see 3 pi terms we will get. So n minus 3 will give you n is equals to 6, so m is equals to or r is equals to 3. If you minus them, you will get 3. So we will get 3 pi terms. So when you will solve all the way the method we have discussed in the previous lectures, so you will be able to find out 3 pi terms, and those 3 pi terms would be this, this and this. So the drag force is the dependent variable, so this is in this pi term. So the drag force is a function of W over H into this is the another dimensionless variables. So here are the 3 pi terms for this particular problem or for the case. Okay, so this is the dimensionless parameters in the form of function, in the form of pi function. Okay, so this is for the real case problem. This is for the prototype, this dimensionless parameter for the prototype. So let's write down the same for the model. So this one I am going to write down for the model. So dm, instead of d we are going to write down dm, wm square, rho m and vm for the model. This is same for the model and this is also for the model. So now this is for the prototype and this is for the model. So basically what is the objective of doing all that? We are going to design a model. Okay, what should be the size of the model? Suppose if you have a object 100-meter length and that you have to make it or you have to make it 100-meter length and 100-meter width. So what should be the size of the model? Okay, so that we cannot just take it as it is. So we have to find out the size of the method by using some engineering way. Okay, so now this is the way to develop the model. So here the pi term you have developed, so write down the same pi term in the form of model. Okay, so here when you compare pi 1, so compare pi 1 with the pi 1 model, pi 2 with the pi 2 model, pi 3 with the pi 3 model. So this will be pi 1. So here you can see this will be equal to pi 1 is equals to pi 1 model, pi 2 is equals to pi 2 model, pi 3 is equals to pi 3 model. So we have write down in the form of equivalency, okay, or in the form of similitude. The size of the model will be, okay, the size of the model will be, so what would be the size of the model? So here you can see these two terms here. So this is width, this is width, this is height, this is height. So that's why we are saying it is size. Size, whenever we talk about the size means the dimensions. Okay, so here width of model will be equal to height of the model divided by the height of the real the prototype and the width of the prototype. So here is the height of the model and height of the prototype. So that's why this we are calling it the size of the model. So if you know the, so here the width of the model is equal to height ratio multiplied by width of the prototype. Okay, so next here you can see the here we are free to establish any of the height ratio. So this is basically hm over h is equals to height ratio. Okay, so the required velocity for the model is obtained from the relationship. Okay, So here you can see, here we have a velocity factor V of prototype and V of model. Okay, so density of prototype, but since we are talking about the velocity, so here is the velocity of prototype and velocity of model. So here is the term. So when we find out the velocity of the model, okay, what should be the velocity of the fluid acting on the model, so that is basically Vm is equals to rho m over mu, mu m over mu, rho over rho m, w over wm, and v. Okay, so here the required velocity for the model is obtained from the relation. Okay, so here also we have a different ratios. Okay, the viscosity ratio, the density ratio, and the width ratio. Okay, so if you know all that, if you know the width ratio, this and this, definitely you know, based on that you can calculate the velocity of the model. Okay, the velocity of the model. So the predicted equation for the drag force of the prototype will be, so here this is the drag force, so you can also find out the drag force of the actual drag force or drag force of the model if you know all those ratios. Okay, so width ratio you can get it from here, density ratio you can get it from here, velocity ratio you can get it from here. If you know all that, you can easily determine the drag force by this method, drag force of the model or drag force of the real life problem. So here you have to note down few things. Note that when we equate the pi terms involving length ratio, we will get geometric similarity between the model and prototype. It means that model is the scaled version of the prototype. So I will explain in the next slide that what's the meaning of the scaled version and what is the meaning of geometric similarity. But here the point to be noted that in the first term, whenever when we here you can see this is called basically the geometric similarity. Okay, the pi terms involving length ratio, because here you see the pi terms are involving length ratio, so this is called a geometric similarities. In the next, with geometric similarity, if the velocity ratio and acceleration ratio are constant throughout the flow field, we say that the kinematic similarity between the model and the prototype. Okay, the pi terms are involving, okay, the velocity ratio. Okay, so that in that case we can say that the model is in kinematic similarity. Okay, so in the next term, when the pi term like Reynolds number or any other number involves force ratio are same in the model and in the prototype, we say that dynamic similarity exists between the model and the prototype. So here one thing is very important to know that, so in the previous lectures we have discussed about the many dimensionless numbers, because whenever we solve the real life problem with the help of different variables, we always get some repetitive dimensionless group. So based on that we have assigned a specific name to each of the group, and here we can see there is a group, there is a dimensionless number, we assign a name to it, that is called a Reynolds number. So what is the Reynolds number? Reynolds number is equal to rho, here you can see this is basically a Reynolds number. Okay, rho VW over mu. Okay, so this number is called Reynolds number, and this is basically helpful to verify the dynamic similarity. Okay, so here we are saying when the pi term like Reynolds number or any other number involve force ratio are same in the model and in the prototype, we say that the dynamic similarity exists between the model and the prototype. So to have a complete similarity between the model and the prototype, we must maintain geometric similarity, dynamic similarity and kinematic similarity between the two systems. So if any of the model fulfill all the requirement of geometric similarity, dynamic similarity and kinematic similarity, we can say that the model is exactly behaving like a real life object or prototype. So here now we are going to discuss the now we are going to discuss the geometric similarities and the kinematic similarity, where exactly it is, just for a physical understanding of that, and the dynamic similarities. So before that, here you can see some of the properties related to geometry and the kinematics and the dynamics. So whenever we deal with these dimensions, these are called geometrical quantities, these are the kinematic quantities, and these are the dynamic quantities, and these are the quantities related to the fluid properties. So now let's see the three basic laws of similitude that has to be fulfilled to behave a model like a real life object or prototype. So a similitude analysis is done to make sure that the results obtained from an experiment can correctly be transferred to the real flow field. Okay, so three basic laws of similitude must be satisfied in order to achieve complete similarity between prototype and model flow fields. So what are those three similarities? So number one, the geometric similarities. What is the meaning of geometric similarities? Here you see, model and prototype must be the same in shape but can be different in size. Okay, so this is the main thing. The size is different but the shape is same. So all linear dimensions of the model must be related to the corresponding dimensions of the prototype by a constant length ratio. Okay, that is LR. Okay, so it's usually impossible to establish 100% geometric similarity due to very small details that cannot be put into the model. So modeling surface roughness exactly is also impossible, because the finishing of the real life object and to maintain the same finishing of a model is really a challenging task. Okay, that we can say that almost it's impossible. So but we can say the linearly, okay, so it should be linearly similar. Suppose if the ratio is 1:10 or 10 times, that means if it is 100, if it is 10, it is 10. Okay, so if it is everything is going to be reduced with 1:10 ratio. If this is, if this radius suppose is 10 meter, suppose if the radius is 5 meter dia, so it has to be reduced with the 10 with the 1:10 ratio. So you can see the shape is exactly the same, okay, but the size is different with the same ratio. So everywhere there would be a size will be same. Okay, but here you can also see there is another aero profile, or there is a wing of the wing of the aeroplane. Here you can see this is 1:10 ratio. Okay, so if this is 8, this is 0.8. If this is 40, this is 4. If this is 1 meter, this is 0.1. Okay, but the angle will not reduce 1 is to 10, because the angle will be same, because if you reduce the angle with 1 is to 10, so the shape will be changed. Okay, so the angle will not vary, angle will be the same. Okay, and every single detail will be in the same location, and it will be shrink with the 1 is to 10 ratio. Okay, so you can see whatever is the point is mentioned is going to be on a same point. Okay, this is on the same point and it will shrink accordingly. Okay, so this is for the prototype. This is a real life shape or size, and this is the model. Okay, but it is reduced in 1 is to 10 ratio. So in the same way it has to be reduced with the length ratio LR. Okay, in the same way the kinematic similarity. In kinematic similarity, model and prototype flow fields. Okay, so here we analyze the velocity and acceleration. So the model and prototype flow field are kinematically similar. If the velocities at corresponding points are the same in direction and differ only by a constant factor of velocity ratio. Okay, so here we are talking about the velocity ratio. The direction must be same. Okay, the shape of the every streamline must be same. The distance between the every streamline must be maintained with the velocity ratio. Okay, so here this also means that the streamline pattern of two flow fields should be differ by a constant scale factor only. Okay, so VR. Okay, so here you can see there is a streamline, here you can see there is a streamline, but the point A and point B must be same. The magnitude of the velocity must be reduced only with the velocity ratio. Here you can see the streamlines and the gap between the two streamlines. Here you can see the gap between this streamline and this streamline. This is the proof for the prototype, and here you can see the gap between the two streamlines are constant. Okay, so it is the size of the object is reduced, so the gap between the object and the streamline is also reduced with the same velocity ratio. Okay, so here, so this is called the dimensional, this is called the kinematic similarity, if the direction of the velocity and the shape of the streamline is maintained everywhere. Okay, so next is the dynamic similarity. So two flow fields should have force distribution such that identical type of forces are parallel and are related in magnitude by a constant factor of force ratio. Okay, so here we are talking about the force ratio. Okay, if the force is reduced for a model with a force ratio, that means the model and prototype will be dynamically similar. So if a certain type of force, that is compressibility force. Okay, compressibility force means the density of the fluid. Okay, so then the density of the fluid will compressed. Okay, is highly dominant in the prototype flow. Okay, it should also be dominant in the model flow. Okay, if the compressibility force is strong in the case of prototype, so it should be strong in the model flow as well. How suitable would it be to use a water tunnel to study the aerodynamic force acting on a supersonic missile? Okay, so to get a high resistance instead of air, we are using a water to test the supersonic missile. If a certain type of force, that is surface tension force, is negligible, is small in the prototype flow, so it should also be small in the model flow. Okay, so how suitable would it be to use a very light and very small model to test the force acting on a ship. Okay, so this is exactly the same. If the size of the to test a model, if the size of the model is reduced, okay, so definitely the amount of force will also be reduced with the force ratio. Okay, so here you can see if it is a uh, natural free jet flow. Okay, this is a big reservoir, and this is a weir. Okay, and here the water is, there is a free jet flow, but here you can see the magnitude of the force is more, because this is our real life case, and this is our model. Okay, so here you can see the magnitude of the force is bigger, the magnitude of the resultant force in prototype, and this is the magnitude of the gravitational force, the Fg. This is the magnitude of the frictional force, and this is magnitude of the inertia force. Okay, so when we combined all those forces, okay, we got a resultant force, that is Fp. Okay, so here you can see all the magnitude of all the component and direction of all the component, okay, correspondingly reduce with a particular force ratio, but the direction of all the forces are same. Okay, and the magnitude of these force are reduced with a particular force ratio. So in that case we can say the system is dynamically similar. Okay, so here, to establish dynamic similarity, we need to determine the important forces of the prototype flow and make sure that the non-dimensional numbers related to those forces are the same in prototype and model flow. Okay, so normally to develop a dynamic similarity, we took help directly from the dimensionless groups and numbers, and those dimensionless numbers are same for the prototype and for the model. So rest of the topic we will talk in the next lecture.